So yes, as Charlie says, I'll be giving 3 lectures which are all broadly speaking on the use of geometric integration methods in the context of PDEs, and I'm going to give 3 actually quite different lectures, so each will be fairly elementary and will be kind of fairly broad in scope. So today I'm going to talk about variational methods. Tomorrow, on Wednesday, I should talk about moving mesh methods in 1 dimension in the context of blow-up, and on Friday I should talk about optimal transport. But today I want to talk about discrete variational derivative methods, and I'm very aware of the fact that there are extremely expert people in the audience, and I'll try and highlight their work as we go through. And it's a pleasure to say that this is a collaborative work with my friends in Japan, Takahiro Yaguchi and Daisuke Furihata, and they've written some very nice papers and books in this work. So let's think a little bit about the context of this conference workshop, indeed this program as a whole. So the program is basically to look at methods, numerical methods, which are structure preserving for differential equations in the broadest sense of the word. And my interest is, broadly speaking, in PDE, so I'm going to look at sort of PDEs which have this sort of general structure, which is, I'm not going to be very precise at this stage. We'll be looking at several examples. Some time derivative here and various spatial derivatives over there. And the purpose of geometric integration methods is, broadly speaking, to find numerical methods which respect qualitative features of the PDE and to analyse those methods in the context of those qualitative features. Now, PDEs are vast, it's a huge, huge subject. What do we mean by qualitative feature? Very many different things. So what I'm going to look at today is qualitative features associated, broadly speaking, with variational structure in PDE. I'm not sure how many of you know about variational structure, so I shall take you through some of that. That's in turn linked with things like gradient structures and in turn conservation laws. So that's the general scheme of things. And on Wednesday I'm going to have a look at scaling structures in PDEs, which links a bit more with the Lie group work that Liz was just talking about. Okay, so as I say, we can't preserve all of the structure in a PDE. Generally, the only numerical method which preserves all of the structure is one which gives you the exact solution for the PDE, and that's kind of not the point. So what I'm going to do is we're going to look at this specific method, the discrete variational method, and my talk will firstly show what this method's all about. Then we're going to use modified equation analysis to understand some of the structure behind this method and use that to derive things like conservation laws and so on. And if I have time, I'll show you how I can use these methods in a particular example to deduce the existence of soliton solutions of certain types of PDE. Okay, so just to whet your appetite, where I'm heading towards is solving KdV, and on the left we have some initial data in blue, and the sort of solution you might get for the KdV if you use a typical numerical method designed to have low truncation error but not preserve solution structure, and it gives you something which isn't particularly nice. And in contrast, the discrete variational methods, which I'll tell you a bit about, give you a much nicer structure because they are based on the underlying structure of the PDE rather than the numerical idea of getting a low truncation error regardless of the underlying structure. So that's a kind of advert for the talk, and in fact for all my talks and maybe for the whole of this workshop. Okay, what we should be aiming at. So let's set the scene, and I do apologise that this is really first year undergraduate level, but well, maybe second year, but just to sort of say the context. So my interest is in looking at PDEs which have a variational structure. So to start with, we assume that we have some function g of u and ux, or higher derivatives, and we define the variational derivative of g to be the integral, the quantity which when integrated gives the difference in the solution there. Very fundamental concept, goes all the way back to Euler when he derived the variational calculus, and the variational derivative, if g is just a function of u and ux, is the well-known Euler-Lagrange derivative of gu minus d by dx of gux. So that's the variational derivative. We'll look at a discrete version of this in a minute. And I will define a PDE to have variational form if it has the structure du by dt is some differential operator acting on the variational derivative. Okay. And the nice thing about this is that lots and lots of PDEs have exactly this sort of structure, and a lot of the features, the qualitative features of that PDE are a direct consequence of this structure. So if we can preserve that structure numerically, there's a reasonably good chance that we'll get qualitative qualitative properties coming along essentially automatically. So that's the basic idea here. So let's give you some examples. The simplest equation of all, the heat equation, du by dt is d2u by dx squared. This has many different variational forms. It's such a simple PDE you might expect that. One of which is you take g to be u squared over 2, the variational derivative is just u, and then ut is like this, and in this case alpha equals 2, alpha being even. Important. Equivalently, we could have g of u being ux squared over 2 minus of that, and then ut is just variational derivative like that, alpha being 0, again even in this context. So that's the heat equation. The KdV equation, somewhat different. Its variational form, well again it has many different forms, but here's a typical g, and then u takes the form of du by dt as single derivative with respect to x of that variational derivative. In this case alpha equals 1, which is odd. And we'll find even and odd have different properties, both numerically and analytically. Current-Hilliard equation takes the same sort of form, but now alpha equals 2. One of my favourite equations of all time, which I shall come back to on Wednesday, is the Swift-Herrenberg equation, which is a fourth-order equation, which again has exactly this structure, but with alpha is 0 and g this form here. So my point is, lots of interesting PDEs have a variational form, sometimes with alpha even and sometimes with alpha odd. Okay, so the variational structure you get with PDEs is intimately associated with whether they have dissipation properties or conservation properties. And here is a kind of sort of base theorem for the whole of the show. So if alpha is even, then this property dj by dt, j being the integral of g, is decreasing, well, is negative, so j is decreasing. And if alpha equals 1, then the same thing is constant. So you have either dissipation or conservation of this integral quantity. And the proof follows completely directly from the structure of the equations. You just assume boundary conditions which make it work. So Dirichlet, Neumann, or periodic, or anything on asymptotic on the real line. All you do is take the definition of j, differentiate, apply the calculus variations, faff around a bit, and it all drops out at the end. So the conservation or dissipation follows very, very directly from the variational structure. So as dissipation and conservation is a useful thing to have, qualitatively we'd certainly want to preserve that in a numerical method, and therefore if we can build the sort of variational structure into our numerical method, the chances are we'll reproduce the consequences of this theorem. It turns out you can do a lot more than that. I mean, this theorem is just the start of the sort of properties that these sort of systems have. So let's talk about the discrete variational derivative method, which I worked on along with my colleagues from Japan, but I will advertise immediately the work of Elena Brynjolf and Reinout, so the discrete gradient method is essentially very, very similar to this, and I hope I can give you... Sorry?
Robert.
Oh, Robert! Sorry, Robert again. I apologise. Robert McLaughlin should be there as well. I do apologise. Thank you. So there's a lot of similarity between what they've done and what I'm going to talk about. So the aim of the discrete variational methods, or discrete gradient methods, or discrete variational methods, is to try to reproduce this sort of variational structure in the context not of the continuous system, but of a discrete system. And the idea is really quite a simple one. We're going to have, in the fully discrete context, I'm actually going to mostly talk about the semi-discrete context in this talk, but in the fully discrete context, we have some discrete approximation to my true solution, and we'll have a discrete approximation GD for discrete of my underlying function g. That was the thing that we took the variational derivative of. And we're going to replace integration and differentiation by their discrete equivalents. And then we're going to sort of start to build up a discretization of the PDE, which makes use of these sort of things. So we define our discrete energy J to be typically the trapezoidal sum of my discrete G. Trapezoidal has very nice properties, one of which is that it's essentially exact for periodic functions, which is a really useful property. And we define the discrete variational derivative by this identity. So if I have u and v, and I substitute them into this, then the difference of the j values will be defined to be equal to this discrete variational derivative here times the difference. And that is how I define it. So that is a discrete analogue of the continuous definition. And then if alpha equals 0, for example, the equation du by dt is variation of g with respect to u gets replaced by this discrete equivalent here, that the time difference in u is then this discrete thing here. So that's essentially the basis of the method. We'll develop that further, but this is the basic idea behind these sort of methods. So just some useful results. These are results any numerical analyst should be quite familiar with. We'll just define the forward and backward operators and central operators to be these things here, the second difference here, and then the trapezoidal rule has integration by parts type results. Essentially integration by parts more or less walks straight over in the context of these operators here, and this is sort of discrete Green's thing here. So these are sort of useful results you can very easily derive. They're nothing more than just counting indices basically, and that comes in very useful to later analysis. So just again to say, there's my discrete variational derivative definition. There's the discrete variational derivative method. And here's the clever slide. This is the one I have no responsibility what's for. So anyway, I didn't do it. This is my great friend Furihata. Several pages of closely worked algebra, says that if G has this very general structure here, so it's a function of u, a function of its forward derivative, its backward derivative, and we make various other definitions, then you can actually write down the discrete variational derivative in this context, and it's this wonderful mess here. Okay. Now, suffice to say, no human being should ever use this formula. This is something you code up in an algebraic manipulator and shove everything in and wait for it to give you something out at the other end. Okay. Why is this true? Well, there are many pages of algebra in Furihata's book, which you can read to convince yourself, but it's basically a large amount of index counting and use of summation by parts and all stuff like that. But the bottom line is if you give me a G, I can get this thing here, and therefore I've got a method, and therefore I have a way of producing a method for solving differential equations in quite general variational form using this famous formula. Well, I won't darken your eyes with this anymore. We'll have a look at some simple examples. If we take the nonlinear heat equation, which is, has g of this sort of form, we can discretize the derivative operator by this forward and backwards average here, and the discrete variational derivative of that, if you go through all the algebra, turns out to be this. And if you look at the heat equation with alpha equals 0 and you plug that in, you get nothing more than the Crank-Nicolson method. Okay, we've been using the Crank-Nicolson method for many years. I was informed the other day that it should be the Nicholson method, and that Crank was her supervisor. But anyway, whatever, it's called the Crank-Nicolson method. We know it's got good properties, and one of the reasons it's got nice properties is that it's based on this variational sort of structure. Okay. You'll notice, like most of these methods, it's implicit. Okay. More generally, if we have a differential equation with the sort of full variational structure here, then the discrete variational derivative method has the same left-hand side. We have the same operator here, and now we simply replace that by the central difference operator to the right number of alphas. And an example that we'll return back to at the end of this talk in quite some detail is the KdV equation. So there's the KdV equation discretized according to this method here. And again, you'll notice that this method is implicit over here and over here. And this is true of many geometric methods. If you want to retain nice qualitative features, you have to pay the penalty of solving a nonlinear equation. But there again, I think that's generally a penalty worth paying. Okay, so that's the KdV. Key feature of discrete variational derivative methods is that the theorem which we proved for the continuous case walks straight over to the discrete case exactly, in the sense that the theorem's the same and the proof is essentially the same. So the theorem says that if I construct my J, then J is basically monotone if increasing or decreasing, increasing if alpha is 0, decreasing if alpha is 2, and constant if alpha equals 1. And again, the proof is very straightforward. You look at the difference. Well, the difference is precisely this by definition of the method, which is equal to this by definition of the method, and then by summation by parts, you get the result. So the discrete variational equivalent of the main theorem exactly reproduces the main theorem because it's based essentially on the same idea. But as I said, we're going to get a lot more out of these methods than just this approach, and that's going to come from using modified equation analysis, which I'll talk about later on in the talk. Okay, so let's have a look at a few more examples, just to show that the method actually works. So here's the nonlinear heat equation. Du by dt is uxx plus u cubed. The g which works for that in the continuous case is this. And if you go through the kind of Fourier-Harter approach and discretize, you end up with this thing here, which looks a bit of a mess, but actually isn't so bad. Although it's nonlinear, you've got a lot of information that you can use to predict into the solution. In the lecture on Wednesday, I'll talk a bit more about how you can solve these and how you choose your time step to make it work. But this sort of method gives you a reliable method of solving this equation, which computes into singularities. If you want to take the Swift-Herrenberg equation, which was this fairly fearsome looking beast, again, this is the G that works for that in the continuous case, and in the discrete case, it actually boils down to quite a simple formula. The discrete variational method for the Swift-Herrenberg is this thing here, where f takes this structure here. And again, we need to solve this using some nonlinear solver, but that nonlinear solver will then give you the correct dissipation properties and a large amount of the pattern formation properties that you want for the Smith-Herrenberg equation. Okay, and there's a few examples of the solution. So basically, the discrete variational method is a very systematic way of discretizing a differential equation, which has this sort of conservation properties and dissipation properties that you might want. But the question is, can we go a bit further than that basic theorem gives us? Can we learn more about the sort of structures that you might expect to get from this? And one of the ways into this is to use the idea of modified equation analysis. So what's modified equation analysis? Basically, the idea behind modified equation analysis is to assume that the solution that your numerical method is spitting out, which is basically a load of numbers, are point samples of some function living out there, which one assumes to be nice and regular, which then in turn satisfies a different but modified equation from the original equation. So one of the ways you can sort of start analysing a lot of numerical methods which are attempting to show geometric structure of some problem, such as a time-evolving PDE, is to try to derive the modified equation satisfied by the solution of that differential discrete method, and to then show that that differential equation has the right qualitative properties that you want to get at. A good example is our symplectic methods for ODEs, where you show that the symplectic method has a Hamiltonian structure, but the Hamiltonian is a perturbation of the Hamiltonian of the underlying ordinary differential equation. So one way in then to looking at these sort of discrete variational methods is to try to apply that in this context. So the idea is that we're going to regard the solutions that we're getting out of our discrete method as point samples of some underlying function u, and what I want to do is to find some sort of variational structure which mimics that of the original problem. And it turns out that the sort of structures that you end up getting look like this. So if du by dt is dx to the alpha dg by du, then the modified equation is du by dt is dx to the alpha of some modified g. I shall call that g bar, but you have to do a little bit more than that to get everything to work, and you end up having to put another operator a in front of this, where a has nice properties. Okay, so typically you want a to be positive, definite, symmetric, and in fact a lot of the operators that we're going to look at are smoothing operators, so they knock out high frequencies as well. So what I'm going to try and show you is that the sort of discrete methods that I've been describing naturally lead to modified equations of this form, and then we can start to study the discrete equation by studying the properties of this modified equation here, which is almost a variational form. Okay, it's certainly close enough to do much of what we want, and we can actually use this to derive further properties as well. So that's the kind of the thrust of this idea. And because I'm primarily interested in spatial structures, I'm going to assume most of the time that we can do our time derivatives exactly, although we can apply modified equation analysis in that context as well. Certainly Brynjolf and Elena have written some very nice papers in this regard. So I'm mostly going to look at semi-discrete methods. Okay, so I'll start off with our friend again, the heat equation, and we'll look at how things work in the context of the heat equation, and then I'll generalize it, and then once we've generalized it, we'll have a look at some other equations which make use of the generalized structure. So as I said, the dVdn method applied to the heat equation naturally ends up with the Crank-Nicolson method, which is this. And the Crank-Nicolson method basically is the discretization of this system here using an AVF method. The AVF method is well understood, so if we have a look at this and look at its properties, then we can always derive the sort of structure of the time-dependent case by applying the AVF theory to it. So I'm not going to worry too much about that. So let's have a look at this equation here. And it's interesting that this equation here is repeatedly wrongly described in textbooks. Okay. In textbooks, what generally happens is people look at this, okay, and they say, well, what's this? Well, it's, if you put in u, you get uxx, which is nice because that looks like the heat equation, and then the next term is minus uxxx, 4 derivatives divided by 12, and they say, well, that's the main error term, not realizing that the equation they've just written down is ill-posed and blows up in 0 time. So that's not the right equation to look at when you want to study this. We have to work a little bit harder to get some sort of modified equation and some sort of structure which is going to accurately reproduce qualitative properties of the solution of this equation. So the way to get into this is to think not so much of u, but the Fourier transform of u, and ask how the Fourier transform of u looks when you stick it into that. And what you get, if you look at the Fourier transform, is that the derivative of the Fourier transform is this, exactly what you get if you just substitute in, acting on u hat, and I can divide that by k being the Fourier transform term. If I pull down a k squared and put a k squared in there, then I can replace this operator, well this operator identical to this one, and that operator's, we've got the k squared up there. Now in Fourier transform world, k squared minus k squared u hat is the Fourier transform of u double primed. This is the Fourier transform of what's called the Fayet kernel, which is a function which looks something like that, which is a nice function, nice symmetric positive function. So I have the product here of the Fourier transform of this times the Fourier transform of uxx. So if I transform back, then the equation I get for ut, and this is an exact expression, and there's no error here, is ut is a uxx, where a is a very nice operator. It's positive, definite. Well, I'll talk about its properties in a minute, but a is basically the action of g, which is this function here, convolved with uxx. So if I was just to summarize that, the true equation is ut is uxx, and the modified equation is ut is a uxx, which is g star uxx. Okay. Now the nice thing about this equation is actually a lot nicer than the original one, because this operator here is a smoothing operator. It knocks out high frequencies. So this equation is going to evolve in a kind of nicer, smoother way than that of the heat equation, and the heat equation was pretty smooth already. Okay, so this is my modified equation, and this modified equation turns out to have a variational structure. So let's talk a bit about this operator A. As I say, it's a convolution operator, so it's smoothing, it knocks out high frequencies, it's positive definite because G is positive, it's symmetric because G is symmetric, it commutes with derivatives, so I can take derivatives either side, that's not a problem, and that's a feature of its convolution properties, and it has a square root. And the square root is convolution with h, where h is that. It's the kind of hat function there. So what is there not to like about this operator? There is nothing not to like about it. It's a very nice operator and all sorts of nice properties. So we can start to analyze the performance of my numerical scheme by analyzing this equation here. And no guesses for thinking what we should do. The obvious thing to do is to start seeing whether this equation here has a variational structure. And then from that variational structure, what can we learn about the properties of the numerical method? Well, the heat equation had several variational structures, and so does this equation here. Here's three of them. You basically choose which one you like. I won't go into detail. If anyone's interested, I can give them the preprint about this, which takes you through it. But which variational structure would you like? So we know that the heat equation has the structure ut is variation of ux squared over 2. The change there is that we get this modified g here multiplied by ux, and we get that one, so you could do that one. So, you know, work through the algebra, you'll find that gives you this. And then by applying our earlier theorem, we deduce immediately that this property here, integrated decreases, and that's everything in sight's positive, so that's already a dissipation property. If you prefer, we could have this variational structure here, again with this thing here, and because A is positive, definite, and all that sort of stuff, we get dissipation here. Or if you prefer, we have this variational structure, again mimicking the earlier structure that we had for the heat equation, and now we can deduce that u squared decreases. So all the kind of variational, all the kind of dissipation properties that my heat equation had are inherited automatically by this modified equation. We knew this already because we knew that the dVdm method kind of did the right job in terms of dissipation. That's probably as much as you can squeeze out of the heat equation. It's not the most interesting equation to study in depth, but it gives us insight into where we might want to go to with other equations. So what I want to do, well, the natural thing to do is to ask how we can extend this methodology of producing these sort of smoothing operators which look like, well, which give us the sort of properties that we want. So I shall essentially define the operator an through this, the an acting on the nth spatial derivative of my function u will be defined to equal the finite difference operator up n times acting on u. So that's how we define it, and you can, by taking Fourier transforms, go off and construct everything you want. We've already constructed the operator a2, that's my earlier operator a, which is convolving with this. If you want to look at a single derivative, then the operator you get, a1, is essentially the square root of this. It's not quite, it is, but it's a rescaling of it, and so on and so on. And the higher up the n you go, the smoother the operators get, which is actually kind of nice. Okay, so the next operator you get will kind of have us an more parabolic shape. So we generate all these operators, and then using these operators we can now start to kind of replace derivatives by operators like this, and then start to build up the variational structure that we need. And it gives you kind of a methodical method of building up the modified equation that you then want to study. Okay, so
you have coefficients or non-linearity.
well, the non-linearities will come in as extra terms, and you'll see how these come in.
And a non-constant coefficient?
Non-constant coefficients, good point, and we move on. I'm here for 6 months, so we can have many conversations. To quote Captain Mannering, I was wondering who would spot that. But, you know, that is an issue, but it's an issue generally, and we can kind of deal with that. But non-linearity is not a problem. So a few nice sort of properties of this. If U is periodic on any interval, for example, 0 to pi, you can play all sorts of nice games with these operators. If I take U, apply an to it, and then apply the trapezoidal rule, I just get back to the integral of U, which is kind of weird, but you do. And if I take ux, apply a1 to it, apply u to that, and take trapezoidal, I get 0. These are just nice properties that you can get by a certain amount of playing around with your operators. Yes, Robert?
Follow up on the previous question. It looks to me like you're saying that a finite difference operator is really, or can be viewed as a pseudo-differential operator.
In this sort of context, yeah.
And then, well, it seems a bit surprising that you're now going to get more out of the pseudo-differential viewpoint than what you could have done directly from the finite difference.
Well, you can get insight into extra conservation laws, which is what I want to talk a bit about. I mean, it gives you a structure that you can work with and move on to. And of course, you're right. I mean, you know much more about these things than I do, and that's why it's fun to be here with you for a few months. Okay, so but let's see what we can get out of this, and I'll be interested again very much in your views. So let's see what we can get with looking at a nonlinear problem, which is the classic nonlinear conservation law with periodic boundary conditions. And 3 properties of this are well known. One is that the integral of u is conserved. You just integrate du by dt, and you get integral of fux, which is difference of fu, which is 0. Integral of capital Fu, which is the integral of fu, is conserved by more or less the same sort of argument. You also get the integral of u squared conserved. That's actually somewhat harder to prove. It just involves a bit more faffing around to prove it. The result isn't quite as direct. And when we apply the DVDM method to this, these two are going to drop out pretty quickly. That one's going to be a little bit of work, and now this is where the structure comes in that we'll have a talk about. Okay, so if you apply DVDM to that, you end up finding that what you end up with gives you, essentially you get this discrete equation here. So ut plus fux is 0. You just directly get this, and we're seeing our operator a1 here. What are conserved? Well, the trapezoidal sum of u and the trapezoidal sum of f of u are conserved. Let's prove that. So d by dt of t of u is t of ut. Ut, we know, we just get it from here, is minus t a1 ux. But we had this theorem earlier that t a n u is the integral of u. So that gives me the integral of f of u, which is 0. And so that immediately gives you that tu is conserved. And it is. You just try any experiment, you'll find it is. Similarly, the differential of f of u is this, which is that, which is 0, by this result here. So these kind of results follow instantly. Integral of u squared is rather more subtle. If you take u squared and take the trapezoidal sum of u squared, you'd expect that to be conserved, but it isn't. And it's more subtle. And what you have to do is introduce a modification of that integral. So the modification we're going to use, instead of looking at the integral of u squared, we look at u a inverse u, and that, if you work it through, is this kind of thing here, in terms of all these x derivatives. So this sort of thing here, you kind of get your head round from this sort of structure that you've been building up. Let's look at the derivative of this. Derivative of this thing here is this, and that becomes that because of earlier, and that becomes that, and if g is that, then this is periodic and therefore vanishes and you get 0. So what's kind of cute is that this structure shows that rather than u squared being conserved, this thing here is conserved. Let's give a demonstration of that. If you take ut is u cubed over 2x, with this stuff here, this equation actually starts to become, well, it develops caustics and stuff. It's not particularly nice, which is kind of what you want as a test of the method. If you take the integral of u squared over here, where you take the trapezoidal version of that, you find that it isn't conserved at all, whereas this modified one is rock steady. So the method basically works in that context. Yeah?
Why is that top line better than the observation down below, from the point of view of computing the solution?
Well, that's a sort of matter of taste, I suppose. But I mean, if this is basically showing what the numerical method is actually conserving.
I understand.
And it gives you some insight as to how it's not conserving the thing it's supposed to be conserving. It's conserving something related to what it's supposed to be conserving. And that tells you what it is that it is actually conserving. Whether it's better or worse is a matter of taste, but at least we know what it is conserving.
Yeah.
Okay. Okay, so I thought move on to my final example, which I kind of advertised earlier, which is the KdV equation. So how does the KdV equation work in this context? The dVdm method gives you this discretization, which was the thing I advertised earlier. If you look at the semi-discrete version of it, then you get this. And what's the structure of that? Well, we've got all the machinery now to build up the structure of this. So this is the method we're going to look at. This is its discrete version. I say it's fully nonlinear. So this modified equation basically has this form here. So that's the modified equation related to that discretization that we're going to have a look at. Okay, so various nice features of this already. To answer your question, there's the nonlinearity, so the nonlinearity is in there, so we can deal with that. I haven't put in variable x, but yeah, I accept that's an issue. But that's what we're going to have a look at, this equation here. And one feature immediately jumps out of you at you on this, in that again these operators here, A1 and A3, are massively smoothing operators. So they're not going to let through high frequency oscillation. So that, in the context of KdV, is probably a good thing. So this has a variational structure, again with a certain amount of faffing around. Sorry, those of you who are not English, faffing around means carefully worded algebra over several pages. You get this. Or if you're other people in the audience, probably 2 or 3 lines. Okay, so this is the variational structure of this, where G has this form here, where I've brought in the square root of A2, which is more or less A1, but with a rescaling to it. Okay, so that's its variational structure. What do we deduce from the variational structure? Item number 1, TU and TG are conserved. I won't go through the argument. It's identical to the argument that worked for the nonlinear wave equation, ut plus fux. It's exactly the same argument. Secondly, if you take this and the action of these smoothing operators knocks out all the high frequency terms, which makes things very nice, and that tells me, again using essentially the same argument as worked before, that the KdV equation conserves the integral of u squared. The equivalent conservation in the discrete equation is this thing here. So we've got this nice, strong, again, conservation property there. Let's look at this in action. Okay, so if I take ux0 to be 50 sec whatever, which is a well-known, well, this gives you, in the continuous case, a travelling wave. If you apply the dVdm method as described to that, it propagates the soliton along very nicely. Okay. If we look at the various things that I've talked about, this is the FFT, initial FFT, which is smooth, and as it evolves, we basically keep the low frequency components down. That's essentially noise. Well, it's really kind of small in the context of everything else here. Let's look at our conservation. The integral of u squared isn't particularly nice. It goes up and down. This is largely associated with peaks coming in and out of the domain with the periodic boundary conditions. If we look instead at the modified conservation law, it's steady as a rock all the way. So the theory is working for the KdV. If I take a different discretization, which hasn't got this variational structure but has the same sort of truncation error, this is what I put up earlier. We don't get the same sort of operators acting. We get high frequency terms generated. There we see them in the FFT. It really doesn't do anything like equivalent job. And that's integral of u squared. That's the modified one, very much not conserved in this context. Okay. And you can do other things. So we know with KdV that we have the possibility of solitons interacting and passing through each other. So if I take a solution with two solitons like this, propagating at different speeds, the dVdm method lets them pass through each other all right. Again, the modified conservation law is working very, very well, and the unmodified one jiggers all over the shop. Okay. I'm just going to conclude this talk with a slightly technical thing, but just to show you how you can push these methods a little bit further. When I did my PhD back in the 1980s, I was privileged to be in the group that Brooke Benjamin led. He wasn't my supervisor was John Norbury, but Brooke was very much the leader of the group. Brooke pioneered the study of nonlinear PDE through really very, very clever calculus variation techniques. Well, maybe he didn't pioneer, but he was one of the great exponents of it. In particular, he proved the existence of soliton-like solutions to KdV by using a variational argument. And what he did was he looked at the minimum of this thing here. Forget the A2 for a moment. If you minimize this, subject to integral of phi squared is gamma, you can prove the existence of a minimizer to that, and from that you can go on to prove the existence of a soliton. In the modified scheme, what you do is you take exactly Brooke's argument, you replace it with the modified scheme, which involves bringing in this A2 here. This is the G function. You replace the exact conservation law of u squared by putting in this other operator here. But you get something which looks very, very similar, and similar sort of arguments show that it also has a minimizer. And then you can look at what the equations the minimizer satisfies. You've got a Lagrange multiplier coming in because of the constraints, so it satisfies these two equations here. And if you set phi is the minimizer x minus lambda t, you find that it satisfies the PDE, and therefore this thing here propagates along quite nicely, and that's what we're seeing with our variational method. So essentially you can walk through Brooks' method, which is really nice. Okay, so just to conclude, DVDM methods give a systematic way to discretize certain classes of PDEs which have certain types of qualitative structure and allow us to use the underlying variational theory to get that. Modified equation analysis helps us understand where these structures are coming from and gives me a way of sort of seeing my way through it. I agree with Robert, there may be many other ways of doing the same thing, but it works for me, and allows us to deduce these modified conservation laws or whatever where appropriate. Just to say, we can extend this to higher dimensions. That's what my colleagues in Japan have done, but it's not easy. You have to use a lot of differential geometry. The differential geometry in the cohomology replaces these discrete summation by parts and discrete Green's theorems and so on. So that's what they've done. But I would argue, if your PDE has a variational structure, make use of it. Whichever way you want to do it, but make use of it. Thanks very much. Doug?
Does any of this apply to problems when you have a non-uniform mesh?
You can do it for non-uniform mesh, yes. Basically, non-uniform meshes are the same as uniform meshes, plus a scaling transformation.
That's a structured mesh. You had something like an adaptively one word.
That's fair enough. The sort of meshes I'm familiar with, which have the structured mesh, it will work for. But yeah, if it's really non-uniform, probably not. Yes?
I was wondering if there's anything special about using finite differences to discretize in space.
Oh no, you can do finite element. I can't answer for spectral. I mean, in a sense, a lot of this is spectral, but you can certainly do this with finite element. Yeah. Yeah.
Can you just explain something real basic to me that you mentioned? So what can you tell me exactly what you meant when you said it preserves dissipation? So what I picked up is...
So in a very simple way, if you've got the heat equation, ut is uxx, and you take ux squared over 2, d by dt of that is negative. Okay? So in the discrete case, if you replace ux by the discrete operator, then that's also decreases. Similarly, d by dt, integral of u squared, is negative, and if you replace u by the discrete u, that's dissipative.
When you say preserve dissipation, it just means sort of a qualitative sense. You wanted to make sure it's the right sign.
Yes, it's got the right sign. Yeah.
Okay.
Yeah.
Okay, so the nice thing about this is how beautifully rock solid those conserved quantities are. But it's possible, of course, that some error is going into the spatial part that you're integrating over. Have you looked at the local conservation laws, of which the local ones are?
Yeah, that's true enough. It is sort of averaging out, isn't it? Yeah. So I haven't looked. No, you're absolutely right. So it's taking the whole thing rather than individual thing.
I think it would be interesting.
It would be interesting to do that. Yeah, you're absolutely right.
Well, if I think about a Hamiltonian ODE and I calculate the modified Hamiltonian, then I have a convergence issue, right? I have to truncate my modified Hamiltonian, otherwise it doesn't converge.
Yes.
Do I find these convergence issues somewhere in that?
Yes, I mean the sort of convergence tends to end up with if you look over very high frequency terms. And the nice thing about these is these operators knock out the high frequency terms, and that actually helps with the conversion. The smoothing works in your favour. Yeah. Oh, sorry. Well, it was Christian and then you, sir.
So you have these modified conservation laws.
Yeah.
Do you have any results on the long time behavior, how long they remain close to the real conservation laws? Your pictures indicated that there's no drift away. One of your pictures, another one.
Well, obviously, ultimately, they will drift due to numerical error, but they seem to work as far as I can tell.
But do you have any rigorous theory about that, or is this just numerical experiments?
No, well, that's the theory I've developed.
No, that the modified conservation laws along the numerical solution remain close to the to the exact one.
Yeah. Oh, do they? No, they often don't. The exact.
So they can drift apart, or?
Oh, hang on. The integral of use, yeah, they could drift apart. So that yes, the modified thing will stay constant, but not necessarily. Yes, you're right. I see your point. I do apologise. I
Are there some rigorous results which give long?
Not as far as I know. Okay. No, thank you. That's a very good point. Yeah.
This heat equation with the different formulations of the functional give this different spatial discretizations then?
No, it's the same spatial discretization. It's just different ways of looking at it.
But the end you get it's the same.
You get the same properties. Yeah.
Because
it's the same equation.
So I'm kind of confused with the sample you show for the conservation law. So my understanding there is that the people who does numerics for conservation laws always tells you that you really don't want to preserve the anti-norm of the solution. Because unless you have some dissipation there,
yes,
you'll never be able to capture
yes.
the top.
Well, I say this is a different way of looking at it. So it's basically saying what is being conserved rather than are we conserving, right?
Okay, but my question is, how do your schemes behave when you are approximating a shock? Thank you.
None of these schemes will work all the way through a shock because we just have the resolution. Ultimately, the high frequency terms will come and hit you, but the answer is they don't. But they stop in the right sort of way.
I've got a question. Can you just show us that graph again? The straight line, the rock steady. Sounds like some reggae.
How about that one?
Oh, I'd like to see the straight line. Oh, there's a straight line. Yeah. All right, that's fine. That's good. So my understanding here is that the wiggly curve is the solution of the finite difference scheme.
Yeah, they're both solutions of the finite difference scheme.
Right. The wiggly line is the solution of the finite difference scheme.
Yeah.
And it's plotted at every grid point. In that.
No. This is.
The integral.
We're doing integral.
So you've integrated. You've got some.
It's actually trapezoidal. I should say trapezoidal. Yeah.
And then you've plotted that number as a function of time.
Yeah.
And then the top one, what I don't understand is what is capital U?
Well, again, this is my. It's basically taking my function, the numbers it's spitting out, applying that operator to it, and I do that in Fourier space, so I can basically do it, and then applying trapezoidal to that.
So the capital U is again coming from the numerical solution.
Coming from the numerical scheme, yeah.
From the graph below.
Yeah.
And the A1 depends upon the times.
The A1 is this operator. Yeah.
So it's okay. So you're not actually
constant is the theorem you proved, right?
Yes, yeah. I can show you the proof if you want.
But you're not solving the partial differential, the pseudo partial differential.
No, I'm solving the discrete thing imaging, the discrete thing. What I've done is I've got that KdV discretization, and then I'm solving that to give me numbers, and then
capital U has also got a mesh site. It's not the solution of the.
Well, it's a discrete solution.
Well, in this equation here, you've got capital UT equals AUXX.
Yes, well,
that's the modified.
That's
equation.
the modified thing.
And A depends upon delta x, and that's a partial differential equation.
Yes, but then if you put it into Fourier space, you can do it exactly. And that's how. Yeah. Brynjolf.
In your examples, you always consider as the Poisson structure the powers of the space derivative ddx, right?
Yes, yeah.
Is there a reason why you could not do any other types of? I mean, there are many PDEs which have different skew adjoint.
I don't know. I just haven't tried, but maybe we should talk about that.
It's interesting whether this could be used in modelling.
Yeah.
If you start with discrete problems, one might be tempted to derive the heat equation. But then it may be nicer to derive the ut equals AUXX.
Yeah.
And have something which has some properties which has your conservation property. Right, anyway.
Anyway, we can talk about it. I'm here till Christmas. Well, coffee, I think.